we've looked at one of our first examples of using fast-growing hierarchy type arithmetic on our basic function gadget omega naught, and then putting that into the control slot of the basic level, the ground level, the usual level of the fast-growing hierarchy. And then we put in just the smallest non-degenerate input into that. So let's just take one small step, just see how that expansion works when we put in n equals 3, and just get a sense of how much bigger that's going to be. So what does that do? Let's work it out. So by definition, phi1 at the 2 level of omega naught says go back to your phi1 at the 1 level, repeat it omega naught times an omega naught. And remember, that's something that's desperate for some sort of number to say, okay, I'm a function, I want a number because I want to work out what this expansion is. Well, first of all, I'm just going to abbreviate that with d, because that's just doubling. So I double omega naught times, and then because I'm diagonalizing, this is something that's made to diagonalize and eat this 3, it eats the 3, and that 3 goes right into the iteration slot. Okay, so we're just doubling omega naught 3 times, and so we're just getting something we could totally write as omega naught 8. Okay, so that's just a little bit of arithmetic. So we're not getting, this should seem maybe a little underwhelming. Before we had omega naught 4, and now we're getting omega naught 8. What's the big deal? And so that's what I'm saying here. This doesn't maybe seem qualitatively different yet. Pretty soon we will make how fast this grows obviously blowing up. But here it's not obviously blowing up. Omega naught 8 as opposed to omega naught 4. Well, but I do want to work out just how much of a difference that is. So how do we figure out what that is? Well, omega naught 8 is omega naught 7 plus omega naught. And there's that loose function slot again. And so when you diagonalize that omega naught, you let it see the 3, it just becomes omega naught 7 plus 3. Okay, doesn't seem that impressive. But what is that? Okay, that's activating the iteration. And so that's omega naught 7 plus 2, that function, that level of our phi naught function, 3 times, it evaluated 3 times on 3. So let's just write that out. That's not too hard to write out. It's not a lot of ink or a computer screen. And then let's start writing that out. Well, that's phi naught at the previous level, omega naught 7 plus 1. So that function, and then that's iterated this many times on itself. Okay, so let's do something I'm going to do a lot here, is just temporarily sort of abbreviate things. Let's just call that this number that's getting repeated here, which is both the iteration exponent and the input, let's just call that n, okay? Really important to recognize that that is way beyond anything we've ever seen before. We were just barely scratching the surface of what happens when that's an omega naught 4 and just putting in 2 into it. Now we've ratcheted up to omega naught 7 plus 2, and we're inputting that same number. So we're doing this twice with original input 3. If we were sane, we would stop and just say, whoa, 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 whoa. We need to go back to omega naught 4 plus 1, omega naught 4 plus 2, omega naught 5, omega naught 5 plus 1, and gradually ratchet up to here. But we're not sane, and we'll just go ahead, and we're just going to assume that maybe we can pretend we've put in the hard work to really understand this guy. And then we want to show that even if we can assume we understand that, this is still going to just blow that away. Okay, so again, this is what we're expanding. That's our original thing, phi naught of phi1 to omega naught 3. And now what we can then abbreviate, we're just abbreviating that previous thing we had as take the omega naught 7 plus 1 level of function, repeat it n times on n. Well, how does that expand? Okay, well, so what was n again? It was the concise way to write it was here with 2 applications of phi naught 7 plus 2 level. Well, but then that's going to unpack as some more stuff at the phi naught 7 plus 1 level. So that's our new friend, the phi naught 7 plus 1 level function. That's going to be iterated this many times. So that's a not crazy value of the phi naught 7 plus 2 level on itself. Okay. And so what have we got here? What we've got is we've got this idea of some sort of interesting function gadget. Here it's omega naught 7 with a successor tag, and then we are raising that to a huge power, and then that is what is creating the iteration exponent on another phi naught omega naught 7 plus 1. Okay, so it's getting significantly more intricate when we see this. Okay, what's going to happen here? We're not going to blow out all the details here. Every single application of that omega naught 7 plus 1 is code for a huge iteration of omega naught 7s. And every time we do those expand out to omega naught 6 plus bigger numbers, which of course depend on omega naught 5, omega naught 4, omega, all the way down. Okay. And of course, every time we iterate this thing, and we're iterating it many times, the number of iterations in the next time we do the iteration depends on the previous answer. So it's recursively controlling those iterations. That's pretty fantastic. Okay, so let's just dive in a little more. Well, okay, we say we're iterating the phi naught 7 plus 1 dot function, which I was just saying is immensely powerful. But let's just focus on just the single number, which is how many of times that's iterated. Okay, so in other words, we're diving into the iteration exponent again. Not because it's the only thing that can make it big. Remember, the three things that make this big are least important is this big number here as the original input. Very important is the nature of the function, really what this control slot is. But also pretty significant is what the heck, how many times are we iterating that amazing function? So it makes sense to dive into this as just one aspect, but an important aspect of what makes it big. So we'll dive into that. Let's call that M. And okay, that again, it takes us back because this is the last time we're going to see this omega naught 7 plus 2 referring to omega naught 7 plus 1 repeated, just a measly 3 times, admitted. Okay, but then that's going to be omega naught 7 plus 1, this function we're getting a bit familiar with, and that's going to be repeated this many times, which again uses phi naught 7 plus 1, but here just iterated twice. Okay, whew. Okay, so how about a new abbreviation? Let's say L is that iteration exponent. So we're recursively, repeatedly diving into iteration exponents that then create other iteration exponents that create other iteration exponents. We'll kind of, we're zooming in and then we'll zoom out in a minute. Okay, so that guy, suppose that's the only thing in the world I'm interested in. Okay, that is a phi naught, or is an omega naught 7 level function iterated this many times on itself. Okay, let's call that K. Let's say K is that iteration exponent. That's omega naught 7 plus 1 on 3. Okay, that finally we're kind of getting down to just the bare omega naught 7 level, repeated 3 times. So that expands this way. Okay, now that's a little different because it's not a successor. It's a function. It's omega naught 6 plus omega naught, and that is an open slot that lets us put in this number. Okay, so that's interesting. Instead of omega naught times number plus just 1 or 2 or 3, now suddenly the number of successors we're putting onto it is immense. Okay, so here we've diagonalized that omega naught 7 did a little bit of diagonalization. It yields something that's an immense repeated successor of omega naught 6, which again, really crucial that has an immense hidden power that we haven't unpacked yet at all explicitly. Okay, so let's say, let's call this number J. Okay, that is an incredibly big number. It's already something that is fully at this level of the kind of number we create with an omega naught 7. In fact, an omega naught 7 repeated twice. It's not an omega naught 7 repeated, ungodly number of times, but it is, J is already at a repeated omega naught 7 level. So it is, again, pretty insane to even suggest the idea that we want to think, well, maybe J is something we can just think of as a given. But we're going to be that insane. Okay, so now what we've got is K. Remember, this is already deep in the iteration level, so this is just a very small part of the final calculation we want here. But we can write it as V naught of omega naught 6 augmented with this immense number J successors acting on J. And I'm not going to go much further. I'm just going to point out, okay, how is that going to expand? We're going to take that and say that's omega naught 6 plus just J minus 1, the previous number to that, repeated J times on J. Okay. And let me just break that, just one of those many, many repetitions off. It's the omega naught 6 plus J minus 1 function acting on J minus 1 copies of that powerful function acting on J. And then, okay, wait a minute. That is a successor exponent, but with this complicated gadget as the input. And so that's going to be repeat the previous one. That should be minus 2. Repeat the previous guy. How many times? This many times, which is why this is going in, on itself. And then we would be in for another round. But this time, it would be, if we emulate that NMLKJ story, how many times we're going to have to do that? Once this becomes something with a big successor, we would get iteration exponents determined by iteration exponents determined by iteration exponents. We would have to work through that process J times. And that's just to get the barest understanding of how we create K. Whew, okay, so it gets really hard to fathom there. It gets like fractal zoom to the ultimate power there. Okay. Already everything here is based on the omega naught 6 level. The baseline here is the omega naught 6 level, which is beyond anything we had done before. And it's augmented by J successors, which creates this incredible tower of iterations. Okay. But let's just assume, so let's say that's done. Okay. We spend the next, 2 years and some massive AI helps us understand K. Okay. Let's just remember what happens with that. Okay. Then L was use that number K as both the input and the iteration exponent on the omega naught 7 level. But remember, every single time we apply an omega naught 7, it's going to go back and do the same kind of thing here. It's going to expand in terms of crazy, crazy augmented omega 6s, where the augmentation is K and beyond, which are already way bigger than this J, which was freaking me out for sure. Okay. And then we do the same thing that M is then apply the omega naught 7 plus 1 function L times on L. If you really start unpacking that, it's going to be back to the same story. Like, when was the last time we were unpacking an omega naught 7 plus 1? That was how L depended on K depended on J. And we're doing that, but in the context where the base numbers are already huge. It's already L. And then almost last, N is do the same thing with the omega naught 7 plus 1 again. And then finally, the thing we're trying to create, which is not remotely, we are still so much at the beginning of this story. This is not something that's going to be powerful by our standards in this toward the ends of the series. Then you finally take that incredible number N, you do one more time where you iterate the omega naught 7 plus 1 function that times on itself. And then that's finally this guy. Okay. You can tell here that we've pretty much got the recipes for, we can make this any number you want, and we can certainly make this any number you want. And so even just doing that, it's going to get ridiculous. But we're going to do things that are quite a bit more powerful fairly soon.